My dear students, welcome back. I know. Exams are coming up fast, right? And this chapter, Electric Charges and Fields, can sometimes feel a little, well, tricky. But don't you worry, I promise, by the time we're done here, you're going to feel so much better about it. So, are you ready? Let's do this! Okay, so I'm sure you've all been scrolling through YouTube Shorts, right? And you've seen those videos, the one where someone rubs a balloon on their hair and then, poof, a soda can starts rolling towards it, all by itself. It looks like magic, doesn't it? Like they have some kind of superpower. But guess what? It's not magic at all. It's pure, awesome physics, and it's exactly what we're going to unpack today. So that invisible pole, that magic force, it's all because of one thing: electric charge. That's it. That's the hero of our story for this chapter. And it's not just about doing cool party tricks, you know? This is a big deal. It's the reason you sometimes get a tiny shock when you touch a doorknob. It's even the science behind how huge machines like photocopiers work. Okay, so here's our plan. Quick and simple. First, we'll look at the magic of static. Then, we'll learn the 3 main rules of charge. After that, we'll get into the math with Coulomb's law, the force formula. Then, the mystery of the invisible electric field. And to finish, we'll solve an actual exam question together. Sound good? Cello, let's go. All right, section 1. So, what is this charge we keep talking about? Well, think about it like this. Everything, and I mean everything, your textbook, your phone, even you, is made up of teeny tiny particles. And these particles have 2 flavors of charge, positive and negative. Most of the time, they're perfectly balanced, you know, the same amount of positive and negative. So everything is just neutral.
But when you rub that balloon on your hair, something interesting happens. Some of those tiny negative charges, we call them electrons, they literally jump ship. They leap from your hair over to the balloon. So now your hair has lost some negative charges, which means it's now positively charged. And the balloon, it's gained all those extra electrons, so it's become negatively charged. And there you have it, our 2 types of charge, positive and negative.
Now, this next part is maybe the most important rule in this whole chapter. I call it the golden rule. You absolutely have to remember this. It's super simple. Charges that are the same, so positive and positive, or negative and negative, they push each other away. They repel. But charges that are different, a positive and a negative, they pull towards each other. They attract. Simple, nah? Opposites attract and likes repel. Okay, moving on. So every charge has its own, let's call it a personality, defined by 3 basic properties. And listen carefully, my students, because these 3 rules are super important for your exams. You'll often see them pop up as 1 or 2 mark questions, so let's make sure we know them well.
So what are these big, fancy-sounding rules? They are additivity, conservation, and quantization. Now, I know the words sound a bit heavy, but trust me, the ideas behind them are really, really simple. I'll break it down for you. Just get these 3 words into your head for now.
First up is additivity. And honestly, it's as easy as it sounds. It just means charges add up. Like simple numbers. If you have a bunch of charges together, you just add them. So if you have a +5 and a -2, what do you get? Yup, +3. That's it. Easy peasy. Number 2, conservation of charge. This one's a big law of nature. It says you can't just create charge from nothing, and you can't make it disappear either. It just moves around. Here's a simple way to think about it. Imagine you and your friend are in a room, and together you have 100 rupees. You might give your friend 20 rupees, so you have 80 and she has 20. The amounts change, but the total money in the room is still 100 rupees, right? It's conserved. Same idea with charge. And our third and final rule is quantization. Now, this just means charge comes in fixed packets, little bundles. The smallest possible packet of charge in the universe is called E. Every single charge that exists is just a collection of these E packets. It's exactly like our money in India. You can have 1 rupee, 2 rupees, 10 rupees, but can you have 1.5 rupees? No, right? There's no coin for that. Charge is the same. You can have 1E, 2E, 100E, but never 1.5E. Okay, so we know that charges push and pull, but how hard do they push or pull? Is it just a little tap or a really strong shove? How do we measure that force? To figure out the exact strength of that push or pull, we need a special tool. And that tool is a very famous formula called Coulomb's law. So here it is, Coulomb's law. It looks a bit scary, but it's not, I promise. It just says that the force, which we call F, depends on 2 things. First, the size of the charges. The bigger the charges, the bigger the force. Simple. And second, the distance between them. But here's the catch. It's inversely proportional to the square of the distance. And to make it all work, we use a constant k. So the whole thing is F equals k times q1 into q2, all divided by r squared. And for your exams, you just need to remember that k is a big number, 9 into 10 to the power 9. So let's look at this visually. What is this formula really telling us? It's pretty straightforward. If you make the charges bigger, the force gets bigger. But the distance part is the real game changer. Because the force gets weaker with the square of the distance, it means if you double the distance, the force becomes 4 times weaker. And if you halve the distance, the force gets 4 times stronger. That r squared makes a huge difference. Okay, but wait a minute. There's something a little weird here, isn't there? We're saying that one charge can push another charge without even touching it. How does that even work? How did they know the other one is there? It's like a spooky action at a distance. Let's make this really clear. Imagine one tiny charge is sitting in Mumbai, and another one is all the way over in Delhi. How does the Mumbai charge know the Delhi charge even exists so it can start pushing it? They don't have mobile phones. They can't send each other WhatsApp messages. So what is the secret? This secret is the electric field. Here's the idea. Every single charge creates this kind of invisible, well, a zone of influence all around itself. It changes the space around it. So the charge in Mumbai isn't talking directly to the one in Delhi. Instead, it creates a field. And when the Delhi charge feels that field, that's when it feels the force. The field is the messenger, the middleman. And to help us see this invisible field, we draw these things called electric field lines. Just imagine invisible lines flowing through space. And there's a simple rule. For a positive charge, the lines always point away from it, like sunshine spreading out. For a negative charge, the lines always point towards it, like water swirling down a drain. Just remember, away from positive, towards negative. Phew. Okay, that was a lot of theory, I know. But now for the fun part. It's time to put it all into practice. There is nothing, and I mean nothing, that builds confidence more than solving an actual exam problem. So let's try one. Don't worry, we'll do it step by step, together. But wait, before we solve the problem, let's have a quick look at our formula cheat sheet. Just to refresh our memory, we have our quantization formula, Q equals NE, we have our big one, Coulomb's law for force, and we have the electric field formula. Got them? Okay, good. All right, here we go, a real exam question. What is the force between two small charged spheres? Okay, take a deep breath. This is a very standard question. You'll see things like this all the time. The numbers are given, the distance is given. The most important first step, don't panic. Just read it carefully. Cello, let's do this. Step 1, always, is to write down what you know. What has the question given us? We have Q1, we have Q2, and we have the distance r. Now wait, look at the distance. It's 30 centimeters. We can't use centimeters, we have to use meters. So we convert it to 0.3 meters. So many students forget this, so please remember. Okay, now we write down our formula, Coulomb's law. And then we just plug in the numbers. And after you do the math, ta-da, the answer is 6 times 10 to the power of -3 newtons. But we're not quite done. There's one last little question. Since both of our charges were positive, will this force be attractive or repulsive? Think about our golden rule, likes repel. So it's a repulsive force. They're pushing each other away. Shabash. See, you did it. It wasn't so bad, was it? And that's a wrap on our super quick revision. My dear students, please remember, physics is not about memorizing formulas from a book. It's about really understanding the beautiful ideas behind them. You are all so bright, and you can absolutely do this. Just practice a few more problems like this one, believe in yourselves, and you are going to be fantastic in your exams. All the very, very best.